This is part 2 of the lecture on 1.7 on linear independence, and where we left off, we had just considered what's in the red box here. The columns of a matrix A are linearly independent if and only if AX equals 0, so that homogeneous equation has only the trivial solution. If we have a set of vectors, like if I go back to our definition, V1 through Vp, we can just create a matrix with those vectors as its column, and then we can apply this test to determine whether those vectors are independent or not. That's what we did in the first couple of exercises from this section. So that's sort of like our official procedure for determining whether vectors are independent or not. But we're going to see that often there are shortcuts we can take, so we don't have to go through solving a system of equations. So we're going to start looking at some of these shortcuts. So next question here on the handout is, can a set of just one vector be linearly independent? And the answer is almost always yes. A set of one vector is linearly independent as long as the vector is not non-zero. The zero vector all by itself is a linearly dependent set. So this may seem a little bit weird to you when you see it, but we got to get used to it. So this set of vectors from our definition on the first page could have just one vector in it. Could be just one vector. And just I don't have any examples on the handout, but let's just pick a vector like 1, 2, 3. That is an independent set. And just to relate this to that defining original definition of linear independence, the system you would get is all you can do is you can take x1 times 1, 2, 3 and say that comes out to be 0. Can you see that the only solution is x1 equals 0? So that's kind of like why we say a set of just one vector is independent, because the only scalar multiple, again, a linear combination is just taking a scalar multiple of that one vector. The only way you can get 0 is for x1 to be 0. That is if the one vector is the non-zero vector. If you have the 0 vector, and you say, well, x1 times 0, 0, 0 is equal to 0, 0, 0. Well, any real number is a solution. So there are non-trivial solutions. Since there are non-trivial solutions, we say that the set of the zero vector all by itself is dependent. Okay, so that's our one vector situation. So it's really easy to tell whether one vector is linearly independent or not. Now my next question here, if I can get my handout, there we go. What about a set of two vectors? Can a set of two vectors be linearly independent? And the answer here is sometimes yes, sometimes no, but it's actually very easy to tell. Suppose we have two vectors that are linearly independent, then we can write c1v1 plus c2v2 equals 0, the 0 vector, where at least one of c1 and c2 are not 0. Just suppose c1 is not 0. Then what we can do is we can take one of these terms to the other side, c1v1 equals minus c2v2, and we can divide both sides by c1 to get v1 equals minus c2 over c1 v2. So we needed c1 to be not 0 to be able to do this division. And what this notation is saying is, all it's saying is that v1 is equal to a scalar multiple of v2. So the conclusion is in the red box. A set of two vectors is linearly independent if and only if one is a scalar multiple of the other. So it's actually very, very easy to tell if a set of two vectors is independent or not. So it only works for two vectors, so don't get too excited about this. But I can just look at this set of two vectors and I can tell they're dependent. Why? Because if I take 1, 2, 3, 4, and if I multiply by the scalar 5, I get 5, 10, 15, 20. So the answer to the question why is, well, the second vector is a scalar multiple of the first, and so they must be dependent. Second example, -1, 3, 2, -6. It's a little bit, can be a little bit more subtle sometimes, so just, it's not always obvious. I just try to get from one component of one to the corresponding component of the other by multiplying. So I just say, well, I would multiply -1 by -2. So what happens if I take the entire first vector and multiply by -2? I get +2, -6. I get that second vector. They're scalar multiples of each other, so they're definitely dependent. But here's two vectors, 1, 2, 1, -1, where these two vectors are independent. And I just say the only way I could get from one to the other, just pick one component. I don't know, say you take 2, you would have to multiply 2 by -1/2 to get -1. But if I take the first component and multiply by -1/2, of course I don't get 1 again. So there's no single scalar that I can multiply 1 by to get the other. So they must be independent. And I just want to draw a little picture here in R2 and think about these examples again. -1, 3, -1, 3 is going to kind of point up that way, right? -1, 3, 2, 2, -6 to the right, 2 down -6 is going to point down this way. So here's -1, 3. Here's 2, -6. When two vectors are scalar multiples of each other, they lie on the same line. And another way to word this is the span of the set -1, 3, 2, -6 is equal to the span of just taking -1, 3. So when vectors are dependent, I can remove one from the set, and the span of the vector stays the same. So dependent means it's kind of like one is not necessary for the span, right? But when two vectors are independent, like our 1, 2, and 1, -1 in that example, the span of these two is not going to be the same if I remove one of those vectors. And I could write either one here. So when I remove one, something changes in that span. That's a way of thinking these are independent. They're essential for the span. If I take any one away, the span is going to change. And in R2, since they're not scalar multiples, we just sort of have this image that they point in two different directions, right? Okay, so there's two vectors. Okay, I probably said more than I meant to say about the two vector situation. So some more theoretical considerations. Theorem 8 is very important. Suppose I have p vectors in Rn and p is greater than n. So that's the crucial statement right there. P greater than n means there are more vectors than the dimension of the space. then that set of vectors must be linearly independent. So if you have 3 vectors in R2, if you have 4 vectors in R3, if you have 5 vectors in R4, such a set is always a dependent set of vectors. So any set of more than n vectors in Rn must be a linearly dependent set. This statement's crucial for us. And I'm going to talk a little bit about the proof of this theorem. Suppose we set up a matrix with the columns v1 through vp. Those are the p vectors in the statement of the theorem. A possible picture is going to be something like this. Now, I don't have actual values, so we're just using our imaginations. We're going to have p columns. We're going to have n rows. P is the number of vectors. N is the dimension of the space they come from. So that's like Rn. The system corresponding to Ax equals 0 must have a free variable. Because we have more columns than rows, we cannot have a pivot column for each one of the variables in the Ax equals 0 solution. So since every column cannot be a pivot column in A, Ax equals 0 must have non-trivial solutions. There's got to be a free variable. Ax equals 0 must have non-trivial solutions. So the columns of A are linearly dependent from our result on the previous page. So here's just a very basic illustration. The set of vectors 1, 2, 1, negative 1, 0, 3. If I ask you, is this set dependent or not, there's a shortcut. We have 3 vectors. They're in R2. We have more vectors than the dimension of the space. They must be dependent. Okay. You could go ahead and set up a system Ax equals 0 and solve. It wouldn't be wrong to do that, but that's a lot of unnecessary work for this situation. Theorem 9, any set of vectors in Rn that contains the 0 vector must be linearly dependent, and that shouldn't be hard to remember. If you have a set of vectors where one of the vectors is the 0 vector, you can take a linear combination where you set all the weights equal to 0, except for the 0 vector. You put a non-zero weight on that one, and that's what we're illustrating right here. And then still the linear combination is going to add up to 0 because non-zero times 0 vector is still going to be 0. So we have a linear dependence relationship for that set of vectors. So point is, if you have the 0 vector in a set, the set of vectors is automatically dependent. Theorem 7 comes next. Theorem 7 is quite a mouthful, and I tried to highlight the most important aspect of that. So again, suppose we have a set of p vectors, and part A, this set S of p vectors is a linearly dependent set if and only if at least one of the vectors is a linear combination of the others of that set. That means there's at least one vector that could be removed from the set, and that the resulting set would have the same span as the original set. So this is an important statement for us to contemplate as we move forward. Part B is just a technical point that you don't have to worry about so much. If S is a linearly dependent set, and if V1 is not 0, then there is some J, some subscript, such that Vj is a linear combination of the preceding vectors in the list. Now, the proof is written out here. I'm not going to go over the proof of Theorem 7. I'm just going to refer to this comment at the end, because I think this is a good statement for you to see. So that proof here, you can read through the details on your own. That's optional. just put it there for those who are interested in the theoretical arguments. But this comment is really important right now. Theorem 7 Part A can be reworded for a set that is linearly independent. A set of vectors is linearly independent if and only if no vector in the set is a linear combination of the other vectors in the set. That's a real nice way of thinking of what linear independence means. And that's the end of this segment.